Hello everybody. In the last class we looked at the different process variables and the different process parameters which are used to define chemical and biochemical processes. Today we will be talking about the fundamentals which are required for performing material balances. So, before we start performing material balances, we need to understand the terminologies which are associated with material balance calculations. Systems and surroundings are the terms which are always used to define the system of interest and whatever comes around it. A system is defined as any arbitrary portion of a whole process or the entire process itself that you are interested in studying. The limits are established by something called the system boundary. Types of systems can be classified as closed systems or open systems. When no mass exchange happens between the system and its surroundings, it is called a closed system. When material crosses the system boundary, then the system is called an open system. Surroundings are everything that is outside the system boundary. The boundary is an arbitrary line which is drawn to enclose the system which we are observing. Processes can be classified based on whether material crosses the system boundary or not. A batch process is one where no mass crosses the system boundary while the system is being observed. So, any material which is required for the system is fed before the observation starts, and after the process completes, the final output is taken out. So, during the time of observation, materials do not cross the system boundary. You also have something called a continuous process where there is a continuous input to the system and a continuous output which is taken out of the system. You can also have semi batch processes which either have an input or an output. Fed batch is a special type of semi batch process where you have only the input and no output. Processes can also be classified based on changes to process variables. When the process variables do not change with respect to time, the system is said to be at steady state. The process variables which are looked at are temperature, pressure, volume and flow rates. You can also have transient or unsteady state processes where the variables will change with respect to time. Batch and semi batch processes are almost always transient or unsteady state processes. Can you think of a reason why? Because in batch or semi batch process, one or more of the variables will change with respect to time. For example, in a semi batch process, you would be having only an input or an output, which means the volume will have to change or the pressure will have to change. You can have continuous processes operating either as steady state or as unsteady state processes. Let us look at a few example problems which can be classified based on the classifications which we looked at. So, the first process is filling a car tire with air. So, here you have air entering into the tire. So, the system has a boundary which is crossed by the material. So, which means the system is an open system, and you have only an input and you do not have an output, which means the system would be a fed batch, which is a special case of semi batch process. Pressure or the volume will be changing with respect to time, both of them could also be changing. So, the process is an unsteady state process. Let us look at a second example problem where you have water flowing through a smooth pipe of a fixed diameter. Here again material is crossing the system boundary. So, the system is an open process. You have both an input and an output, which means it is a continuous process, and this is a steady state process as there are no changes to the process variables. Let us look at a third example, which is a bottle of cold juice left on the tabletop. So, here material does not cross the system boundary, which means it is a closed system. Again, you do not have any input or output, which means the process is a batch process. Then you have changes with respect to time with temperature. Because it is a cold bottle of juice which is left outside at room temperature, the temperature of this juice is going to keep increasing. Therefore, the process is an unsteady state process. Okay, let us look at a little more complicated example, which is the flush tank in a toilet. Based on the time of observation, this system can actually exist as an open or a closed system, a batch or a semi batch or a continuous process, and a steady state or an unsteady state system. So, this is because when you observe it, the system could actually have different inputs or outputs, and there could be a change in volume or there could be a steady state operation. When you turn the flush tank on, the water keeps coming out, which means the system becomes an open system, and there is also a semi batch system. During this time of flushing, you could also have water coming in, which would make it a continuous system. However, after the flush tank has emptied and you only have the refilling, then it could be a fed batch system. So, once the flush tank is full, it could just be a batch system where no material is crossing the system boundaries. So, the system can also exist as steady state or unsteady state depending on change in volume with respect to time or change in temperature with respect to time. So, why I chose this example is for you to understand that a system could exist in different states depending on when it is being observed. So, the fundamental concept on which material balances are built is the law of conservation of mass. Mass cannot be created or destroyed, it can only be changed from one form to another. Total mass of a closed system will always have to be a constant. This is based on Antoine Lavoisier's discovery in 1789, which showed that mass is neither created nor destroyed during a chemical reaction. He observed that the mass of the reactants was equal to the mass of the products. So, this provides the fundamental basis for performing any material balance problem. What is a material balance? I keep talking about performing material balances. What do I mean by that? Material balances are nothing but writing an accounting for materials. We know that total mass of a system has to be conserved. So, we need to understand what could happen to the material which enters into a system so that we can write a balance sheet for materials. Let us see what can happen when a material enters into the system. It could either leave the system, or it could stay back in the system, or it could get converted to other materials in the system. In this case, the input material will be consumed and new material would be formed. So, based on this understanding, here are the terms which we would be using in the material balance equations. Input, which is the material entering the system, output, which is the material leaving the system, and accumulation, which is the material which is staying back in the system, and generation, which is the new material which is being formed in the system, and you also have consumption, which is the material that is consumed in the system. So, we need to come up with an equation which will correlate these 5 terms. So, this general equation which fits for both material and energy balances is as follows. Accumulation is equal to input minus output plus generation minus consumption. So, this equation forms the basis for performing all material and energy balances, which we will repeat throughout this course. As part of this course, this is the fundamental equation which we will try to apply to simple systems and then try to understand how the same equation can be applied for much more complicated systems, and using systematic approach to solving the problems, we would be able to break down even the most complex processes into very simple steps by applying this particular equation and performing material and energy balances. So, to start with, we will look at how to perform material balances. Here is an example of a very simple system. This is the same system which we used as an example to classify the processes which we were talking about. Calculate the accumulation of air in a tire which is being filled with air at 150 grams per minute. For this system, the input is at 150 grams per minute. You do not have any output, there is no generation or consumption because there are no reactions happening in this system. So, your accumulation equation is accumulation equals input minus output plus generation minus consumption, which means your accumulation is equal to input, which is 150 grams per minute. So, this is a simple example problem which shows how you can account for material which is entering into a system. Let us look at a problem which seems a little more complicated. However, while using the same principles, we will be able to solve this problem with the same level of ease which we had for the previous example. The problem statement goes as shown here. The heart is divided into 2 sides, each with 2 chambers. Blood enters the left atrium from the pulmonary veins and drains to the left ventricle, where the blood is pumped out at an average rate of 70 beats per minute. The stroke volume, which is defined as the volume of blood discharged from the ventricle to the aorta, is 70 ml for each contraction. Assuming that no reaction with blood occurs in the heart and the heart chambers do not accumulate blood, determine the inlet and outlet mass flow rates for the left side of the heart. You can assume the density of blood to be 1 gram per ml. So, using this we can calculate the mass flow rate for the outlet stream. It has been told that the stroke volume, which is the volume of blood which is discharged from the ventricle to the aorta, is 70 ml per beat. So, using this we can actually calculate the volume of blood which is pumped out per minute and then convert this volume to the mass of blood which is pumped out from the heart per minute. So, outlet mass flow rate is equal to stroke volume times beats per minute times density of blood, which is 70 ml per beat times 70 beats per minute times 1 gram per ml, giving you a mass flow rate of 4900 grams per minute. Now, going back to the fundamental equation, we know that we have to identify if there are any generation, consumption or accumulation terms before we can calculate the input term. The question clearly states that there are no reactions happening, which means generation and consumption terms are 0. The question also states that blood is not accumulating in the chambers. So, accumulation is also 0. Plugging these values back into the fundamental balance equation, we get input equals output, which is 4900 grams per minute. So, both the inlet and outlet flow rates are 4900 grams per minute, and this problem could be solved with the same ease as we solved the problem with the air being filled for a tire. Although the problem looks complicated, breaking them down into the simpler terms which form the material balances makes it a very simple problem to solve. Now that we have looked at some of the example problems, let us see how the procedure for performing material balances would look. What type of material balances can we write? For any given system, we can write the total mass balance. The total mass balance is basically the combination of all the components which are present in the system. So, all the materials which are entering and all the materials which are leaving are actually taken into account and the balance equation is written. So, if we were to write a balance equation for this system, we start with input minus output plus generation minus consumption equals accumulation. As total mass cannot be created or destroyed, you would have generation and consumption terms going to 0, thereby you will end up with input minus output equals accumulation. You can also write component balances. So, these are basically for individual components which are entering and leaving the system. You might have multiple components which are entering and leaving the system, and we can write separate balances for each of these components. Some of these components can be non-reactive. When they are non-reactive, you do not have any generation or consumption of that component. However, if the reaction is taking place and the components are taking part in the reaction, then we will have to account for the generation and consumption terms of these components. Last but not least, for a process which is at steady state, accumulation would be equal to 0. When we described steady state, we mentioned that the parameters do not change with respect to time. When accumulation happens, what would happen is some of the components would actually be building up within the system, which means there will be a change with respect to time. So, under steady state conditions, accumulation would be 0, and this is an assumption we will consistently make. Throughout the course, for most of the problems, we will assume the system to be at steady state. This is a reasonable assumption to make because most of the times processes happening in an industrial scale are happening at steady state. Unsteady state processes usually happen as transient processes for very short periods of time, such as startup and at the time of ending a process. Other times you actually have steady state operations. For this reason, for all the calculations which we perform for the material balances and even for energy balances, we will assume the system to be at steady state unless it is explicitly stated otherwise. So, please remember this, and whenever I perform calculations in the subsequent lectures, I will be assuming accumulation to be 0 even if it is not stated in the problem explicitly, because we will be assuming steady state for performing the calculations. So, when we perform material balance calculations, one thing which we would come across is there is a lot of tedious calculations that are associated with each problem, and many a times after performing tedious calculations we realize that there is not enough information in the problem for us to arrive at the final answer. To avoid this, we can actually perform something called the degree of freedom analysis. How do we perform degree of freedom analysis? So, there is a systematic way which you can take to make sure that the problem is actually solvable. First, you would draw and label the flow chart, and then you will ensure that all the information given in the problem has been entered in the flow chart. Then you would go about incorporating the appropriate relationships that are provided. When you have two variables which are related by some correlation given in the problem, do not use new variables, instead write the dependent equations as the unknown. Count the total number of unknown variables in the flow chart, and then count the number of independent equations that you can write which relates these unknown variables. You can actually calculate the degree of freedom as number of unknowns minus the number of independent equations. If the degree of freedom is equal to 0, then you have the same number of unknowns and the same number of independent equations, which means the problem can be solved. There is going to be only one unique solution to the problem. If the degree of freedom is greater than 0, then you actually have more than one unknown which cannot be obtained. So, you have more unknowns than independent equations. So, you need at least NDF number of variables that need to be fixed before you can solve the problem, or you need NDF number of equations to solve the problem. So, when you get something like this, many a times it could be because of an oversight. So, it is important to check if you have missed any correlations or equations and ensure that all the data which is provided to you in the problem has actually been entered into the flow chart that you have prepared. If NDF is less than 0, then there are actually more independent equations than unknowns. Although this does not happen commonly, in some cases you would see this happening. This could either mean that some of the unknowns have been missed while preparing the flow chart, or it is also possible that the problem is over specified, which could mean either there are redundant equations and information provided to you, or it could also mean that there are inconsistent equations which will lead to confusion while solving the problem. So, performing this degree of freedom analysis can actually ensure that the problem you are working on is actually solvable. Now, after establishing that we have a solvable problem, how do we go about performing the material balance problem itself? First, you need to choose something called the basis for calculations. What is a basis? A basis is a number which you choose to make your calculations easier. If amount or flow rate is given, then you would use that as your basis. For example, if you have a problem which states that 1 kilogram of substance A enters into the system, and then you would choose that 1 kilogram of A as your basis. If you have several amounts or flow rates that are given, then you can also use them collectively. If no amount or flow rate is given, then you would have to assume a convenient amount or flow rate as the basis. You can choose either 1 or 100, which would make your calculations a little easier. Choosing an appropriate basis will ensure that the calculations you perform are easy to work with. How do you choose a basis? When you need to calculate something, you need to know what you already have, what you need to find, and what would be the most convenient basis. Answering these three questions will actually give you the best basis for performing the calculations. Once you have decided on the basis, you start drawing a flow chart. This flow chart should have all the known variables, which includes the basis that you have chosen. Even if the basis is an assumption that you have made, please ensure that you enter this value in the flow chart. Label all the unknown variables and write them in the appropriate places of the flowchart. Include each component which is there in the system, on the flow chart itself. Your goal is now to complete the flow chart. So, what you try to do is you will incorporate all the relationships. For example, if flow rate of stream 2 is given as twice that of the flow rate of stream 1, do not write F1 and F2, instead you can write F1 and 2F1. So, this helps you understand that there is a dependency of these two variables, and this will help you solve the problem. Whenever you are preparing these flow charts, ensure that you do not use volumetric flow rates. The reason is volume is not conserved, mass is the only thing which is conserved. So, if you have a change in phase, then there can actually be a significant change in volume without mass being changed at all. Write down what has to be determined. So, once you have all the data from the question which is put into your flow chart, make sure that you also note down what information needs to be calculated. If the problem gives you two different bases, for example, there could be two streams with one stream given in terms of mass units and the other stream given in terms of moles, then convert all of them into one basis. Make sure that all of them either exist as mass or moles, so that you can actually perform the calculations effectively. Perform degree of freedom analysis. Basically, you count all the unknowns and identify the equations, and make sure that the unknowns and the number of independent equations are the same. If they are not, please check the flow chart again. Once you have performed degree of freedom analysis, write down all the equations that are correlating these unknown variables, mark the variables that need to be solved for, and finally solve these equations. This will give you the desired answers. Calculate all the quantities that need to be required that need to be calculated in the problem. So, read the problem carefully and ensure that you have all the values that have been asked for in the problem. In case due to some unfortunate reason you had chosen a number which is different from the value given in your problem as the basis, then you should make sure that you go back and convert these values, convert the final answers you got to the appropriate values given in your problem. This is not a good idea. Never use a value which is not given in the problem as a basis. If you have a flow rate or mass or moles which has been presented to you in the problem, you should ensure that you choose that value as your basis. In case you do not do that, you will actually have trouble with converting the values back, and this could lead to unnecessary errors in your calculation. Please avoid this. However, in some rare situation where you might have overseen what was given in the problem and you ended up choosing a different value, you anyways go and confirm whether these values were the ones which have been asked and whether the values are the ones that have been provided, and then convert them back appropriately. With these fundamentals, you are now equipped to perform material balances for simple systems. So, in the next class we will look at single unit processes without reactions, which are some of the simplest processes for performing material balances. We will look at different processes that can exist, and we will also perform many example problems which will help us understand these systems better.